Swayam Prabha. Digital India. Educated India.
Now, when we are looking for solutions, now that we know is at least one solution exists, so the way we look for solutions is the following. We can talk of many different types of solutions. The first kind of solution is what is called a local minimum. Okay. A local minimum. So, x star in S is set to be a local minimum if there exists a radius r greater than 0 such that f of x star is less than equal to f of x for all x in a ball of radius r around x star and in S. Okay. So, x star is said to be a local minimum if there exists an r greater than 0 such that f of x star is less than equal to f x for all x in a that lie both in S and in a ball of radius r around x star. All right. So, the way what is going on here is the following. Let's look at, let's plot, take an example. So, suppose my domain is like this. Okay, it's this interval here and maybe also and this interval here. Okay, so this is my domain. The feasible region is this blue line thing here, and suppose my function looks something like this. Okay. Now, what is the local minimum here? So, S is this and this, and what I have plotted here is my function f. So, you can see in this picture actually there are two local minima. One is this point here and the other is this point here. This point is not a local minimum. Why is that not a local minimum? It is infeasible, right. So, at the very beginning, a local minimum, the way I have defined it, is an x star in S. So, it has to at least be feasible. Okay. So, this point is an infeasible point. So, it cannot qualify to be a local minimum. This point is feasible, and moreover, if I see that, zoom in and see into a small region around it, the way the function looks is that it has its least value at that point, right. Likewise, this point is also a local minimum around this. If I search, the function has its least value over there. Okay. That does not mean that the function cannot have a lower value elsewhere. All right, that is a completely separate matter. Okay. So, let me give you another example. Just a similar sort of region. let us take S as this and this, and suppose I consider a function like this. Now, this is my function, this is my set S. Okay. So, now can someone tell me what is my local minimum? So, this rightmost point that you have is, this is the local minimum. Okay, let me actually draw the function more completely. So, the function keeps decreasing further. Okay. Yeah. So, why is this rightmost point a local minimum? So, if you look at this, if you look at the function on the entire region, entire ambient space, which is on the on R, then of course the function decreases further. But when we are talking of local minimum, we are comparing only with points that are in S, not points that are outside S. There may be points outside S that may be better than points inside S. That is not of relevance to us. Okay. So, if you look at this point is such that now if I take a small neighborhood around this, a small ball around this, and intersect that ball with S, what I am left with is only this part, and in this part it is the least this point gives you, the right hand point gives you the least possible value. Any other local minimum? Any other local minimum? What is the other local minimum? So, if I take the right end point of the left segment, now again around this I can draw a ball like this. The ball intersects only this part, and in this part this is the least. It is not at all relevant to the optimization problem that the function has further decreased here and so on. All of that is not relevant, because after all we are comparing only with points in it. Is clear? The notion of solution that I mentioned earlier in the first class is what can be better class, is more, a better name for it is what is called a global minimum. Global minimum, so is an X star in S is said to be a global minimum if f of x star is less than equal to f of x for all x in S. It is true. So, what the question here is that, so you are referring, I think, to the right endpoint of the first segment, right? Yeah, of the left segment. Yes. So, if I take a radius r that is very large, then what is going to happen is, say for example, if I take a radius large enough to include all of this, suppose, right, a very large segment, a large radius, then that also you will include also this point, right, and so consequently this will not be the minimum in such a large ball, and this is usually the case. If you make this region larger, you will start discovering points more, you will be comparing with a larger set of points. So, consequently, it is possible that you will find a even better point than the one you started with. But a local minimum, the definition is there should be some neighborhood, however small, okay, some neighborhood of positive radius in which it is the best. Okay. So, there, for me to show that this is a local minimum, all I have to do is demonstrate for you one neighborhood. It need not work for all neighborhoods. Okay. So, a global minimum is defined in this way. So, now come back to our two examples. Can you point out what the global yeah, can you point out in these two cases what is the global minimum? So let's start with this one. Where is the global minimum here? So it's unfortunately my drawing is not that good. So let's assume this one is lower than this one. What is the global minimum? Yeah, it's this point here, right? So this one here, this is the global minimum of the function. Is the global minimum attained in the set? Yes, global minimum is attained in the set. In fact, this is you can see the interval. These are two closed intervals. Their union, that's a compact, that's a closed and bounded set. And the way I have drawn the function is continuous. So the global minimum is attained in this. Okay. Now, global does not mean what the minimum of the function without the feasible region, means the minimum of the function which is over both feasible and infeasible points. That is not what global means. For that there is a different name, that is what is called an unconstrained minimum. Okay. So, I will just unconstrained minimum is simply some x star in Rn this is a completely separate concept. So, the unconstrained minimum need not even be a feasible point. The unconstrained minimum may not even be finite, okay, because you are now looking for the function, how the function for the function even outside the feasible points. Okay, it may even be that the function is not defined on the full region. So, all sorts of things can happen once you search outside the constraint, but assuming it is finite and finite, this is what it is referred to as. Okay, this is the definition. Okay. So, let us come back to the thing that I was mentioning. So, you have a global, I was talking of global minimum. So, what is the global minimum in the first case you pointed out, it is this particular thing here. What is the global minimum in the second? The right endpoint, right, the right endpoint of the second segment here, right, that is your global, that is your global minimum. Okay. What is the unconstrained minimum in each of these cases? In the first case, yeah, this particular point here, this point here, this is the unconstrained minimum. And what is the unconstrained minimum here? It is not attained. It's the unconstrained infimum, the value of the function is 0. If it keeps going this way, it will be 0. It is, but it may not be. It's not necessarily attained. Right? Okay. All right. So, if you see Weierstrass theorem, what it is guaranteeing you is the existence of a global minimum, or it is telling you when a global minimum is attained. Okay. Now, even when Weierstrass theorem is not satisfied, you may have that the local minimum can be attained. Okay, and that is very much possible. So, even though you may not, a global minimum is not attained, you may be able to find local minima that are attained. Okay. So, now let me of a strict local minimum. So, x star in S is said to be a strict local minimum if, so x star in S is said to be a strict local minimum if there exists an r greater than 0 such that f of x star is strictly less than f of x for all x in this ball of radius r around x star and lying in S, except of course x star itself. So, if you compare with every point x that lies both in the ball and in S, except for the point case where x is equal to x star itself, then you will find that f of x star has a value strictly less than f of x. In that case, you say that x star is a strict local minimum. So, again let us do and go through this example. In both of these in both these cases that we have drawn, let us look at the two local minima that we had. Are they, let us check, are they strict? So, this one, is it strict, this local minimum? This local minimum is strict, at least the way I have drawn it, it is strict. You can find it's you can find a ball small enough. This one also, there is a curve here, you can, if you look closely enough, this one is also strict. What about this one, this particular one? This is also strict, likewise this is also strict. Okay. So, these are all strict local minima. So, what does a non-strict local minimum look like? Yeah. So, so what must happen is that, so something like this. So, all these points, they have the same function value. Take a, you take this point, you take this point, you take this point, around them you choose a neighborhood. There will always be another point, there is always another point that has the same value. Okay. This is one way in which this is one way in which you have a minimum that is local, but not strict. Okay. So, there is a very closely related notion, I will write that now, which is called an isolated minimum. Isolated, or precisely local minimum, isolated local minimum. X star in S, X star in S is said to be an isolated local minimum if there exists an r greater than 0 such that x star is the only local minimum in B of x star comma r intersection S. So, an isolated local minimum is one where in which you can find a small radius around that point, such that in that radius there is no other local minimum. Okay. So, now can someone tell me how is this related to being a strict minimum, a strict local minimum? So, clearly an isolated local minimum to begin with has to be a local minimum. Okay. Does it have to be strict, or is strict the same as implies isolated, or isolated implies strict? Okay. So, the answer is isolated actually implies strict. Okay. And the reason to see this is the following. So, when is a minimum isolated? It is isolated when in its neighborhood there is no other local minimum. Okay. Now, suppose if it was not a strict local minimum, if you have a isolated local minimum that is not a strict local minimum, then in that case what would happen? So, let us do this carefully. So, x star, so suppose, so the answer is, I am going to argue that every isolated local minimum is a strict local minimum. Okay. So, this is what we are arguing. So, why is this the case? So, let x star be an isolated local minimum, and suppose x star is not a strict local minimum. Suppose x star is not strict. If x star is not strict, then what does that mean? Go back to the definition. If it is not strict, that means that there must be, then it is just a routine local minimum. Okay. And what does that mean? That means that, so it is a local minimum, means that there exists an r greater than 0 such that f of x star is less than equal to f of x for all x in this neighborhood. Now, if it's strict, then there exists an r greater than 0 such that f of x star is strictly less than f of x for all x except for x star and in this neighborhood, right. So, if it is not strict, then it must be that in this inequality here, equality must be attained for some point, and this must be true for every radius r. No matter how small you make the radius, you should continue to get a point which is in that ball and in that lies in that ball and in S, such that there is equality here, right. So, what does this mean? This means that for all r greater than 0, there exists an x in this, which is not equal to x star, such that f of x star is equal to x. Okay. So, now let's take some radius r. Now, so in that radius r, let's see what's going on. Here's your point x star in this, and here's my so here's my, okay. So, suppose, so I'm just zoomed into point x star, and this is the, so this ball doesn't look like a ball. So, this is my point x star, this is my radius r around it. Okay. And so, suppose here's my set S. Okay. And so, for every radius r, I can find a point x such that f of x star is equal to f of x, a point x in this ball, right. So, here's suppose a point x, that point x. Now, this point x has the value of f at this point x is equal to the value of f at x star. Now, what can I do? Now, f of x star is certainly has lower less than value less than equal to all of these, everything in this radius. Okay. So, what does this mean? This means that, so everyone's following me here. See, remember x star is a local minimum. So, there is certainly a small enough radius in which it is the its function value is less than the function value of all other points. Now, in every radius around x star also there is another point whose function value is whose function value matches with that of f at x star. So, which means that if I take a small enough radius, then in that radius x star is both a local minimum, okay, and there is another point which matches, whose value is the same as that of x star. So, what does this mean? Now, around this other point, now I can draw another small ball. Okay. So, what can that small ball is going to be in that small ball is going to be inside this particular ball, right. So, all these points, their value is going to be is already less than equal is greater than equal to f of x star, but f of x star is the same as f of x. So, f of x is going to be less than equal to the value of all of these small points, which would make x a local minimum, right. So, if x star is not isolated, these new points that you keep finding, they themselves become local minimum, okay, for small enough radius. So, what this means is, this would imply that x for small enough r So, for all small enough r, x is a local minimum. What this means is that x star is not isolated. So, x star cannot be isolated. So, if it's isolated and not strict, we get to a contradiction that it's not isolated to begin with. So, it has to therefore be strict. Okay. So, every isolated minimum, local minimum, is also a strict local minimum. The converse is not true. So, every isolated local minimum is a strict local minimum. That is what we just argued. So, every strict local minimum need not be isolated. So, here is an example of a function like this that demonstrates this. So, I encourage you to go and plot this when you go back home. You can plot this at in MATLAB or something. So, consider this function f of x which equals x to the 4 cosine of 1 by x plus 2 x to the 4. Okay, and let us take this in say minus 1 to 1 except 0. At 0, you define f of 0 as 0. Okay. So, what you will find when you plot this is that this function has many undulations as you go around 0, as you go closer and closer to 0. Okay. But of course, the least possible value is at 0. but you will have many undulations as you go closer to 0. Okay. So, what will happen is that 0 is a strict local minimum, but in its neighborhood are many other local minimum. So, in every neighborhood there is another local minimum. So, it goes like this at 0, but then something like this. So, there are many oscillations all happening at higher and higher frequency as you go here. So, this is at 0, and then in every neighborhood I have zoomed into this, but if you go for no matter how much you zoom in, you will keep finding another local minimum. Okay. So, there will be this local minimum, this local minimum, this local minimum, etc.